Hello, everybody. Welcome back to our political statistics class. This is the fifth week, and we're almost done with all the contents of the class. But we need to move forward, and we're gonna put the bar of the conceptual level higher this week. So for that reason, we're not gonna have a technical lecture. We're just gonna have a conceptual lecture this time. Okay? But I want you to focus on the first report of the applied project. For that reason, I didn't ask you to do anything else or learn new skills in R. I just want you to practice the skills that you have already learned and apply them to the first report of the applied project. And I think it's going to be enough for this time, and especially because we're going to cover so many topics this week about inferential statistics, and it's going to be much more difficult to some extent than what we learn with descriptive statistics. Okay? So I would like to start with this idea that Pollock, or this story that Pollock told us about, what happened with the Literary Digest poll of 1936. It was a crucial time in the American history. The United States was just recovering from the Great Depression. Franklin Roosevelt proposed this New Deal, and what was at stake in the 1936 elections was very high. Was the continuity of this new policy, this policy of welfare state in the United States. So predict accurately what will happen with this election was very important in that time. Okay? And the Literary Digest predicted that Franklin Delano Roosevelt would lose these elections in a very tremendous way, like a 39 against 60% of the votes. That would be something that might have changed the history of the United States for what, not only for the 30s, but the 40s and the Second World War. What would happen without the New Deal? What would happen without the leadership of Roosevelt during the Second World War? That would be very interesting. But what Pollock didn't tell us, or what the book of Pollock didn't tell us, is that there were a pollster, George Gallup, who was able to accurately predict that Roosevelt would be reelected. What explains that difference between the Literary Digest and Gallup's prediction about these elections? That, to some extent, is going to be the topic of this week. Okay, why Gallup was able to accurately predict what will happen with these elections, and Literary Digest not. Okay, so keep that idea in your mind, and we're gonna come back to this idea of the importance of prediction in statistics, in political science, and in practical terms when you want to conduct a study such as a survey. It's very important the quality of the estimation that you make. Okay, so this week is going to be pivotal in our course. If we look backward and we see what we have learned during these past 5 weeks, we should remember that we introduce this concept or this idea of population and sample, which are our objects of interest, and that we, with statistics, with estimate parameters and statistics. Statistics are related with the sample, parameters are related with the population, right? Later we talk about the threats to external validity. That was in the first week. During the second week, we talk about threats to internal validity and how the research design is supposed to deal with that kind of things. And just to remind you, these threats of internal validity is the idea of whether my variable, my explanatory variable, actually explains my outcome of interest, right? In the third week, we talk about univariate descriptive statistics, and we introduce or review these concepts of measures of central tendency, such as the mean, measures of variation or dispersion, such as the standard deviation, and this idea of the shape of the distribution. And in the fourth week, we talk about this, how to use descriptive statistics to control for control variables. Okay? So, to some extent, thematically, how can we relate all these things and how week 5 is going to be pivotal for what's coming next? Okay? So, when we talk about parameters and statistics, we're going to focus especially in some of them, especially the measures of central tendency and the measures of variation. But if we want to move from the sample and to say something about the population, we're going to experience that problem or that potential problem of external validity. If you don't remember well, external validity is this idea or this problem of what might happen if the sample is biased, or even if the sample is not biased, what happened with that step that moving from the sample to the population, and what happened in between is what we call the random sampling error. Okay, so this week we're gonna tackle this idea of the random sampling error much more. We're gonna discuss all the time about the random sampling error, and it's also called standard error. Okay, so we're gonna learn how to use the central limit theorem, normal distribution, the t-distribution, to be able to say something about the population, and that's the main goal of inferential statistics. And with these that we're gonna learn this week, we're gonna be able to run tests of significance and test hypotheses and rival explanations in a more like a robust way that with descriptive statistics. And finally, the 7th week, we're gonna use those elements and we're gonna again talk about the threats to internal validity and how linear regression provides a powerful tool to both inferential statistics and also, and to some extent, to deal with this problem of external validity, but at the same time, to deal with this problem of internal validity. Okay? So that's the roadmap of this whole course. And it's good to have this idea in mind of where are we and where are we moving. Okay? Okay, so the main research question in inferential statistics is how accurately does a sample statistic estimate a population parameter? So you remember this example from the first class. So I have a population here and I have a sample. I draw a sample of 3 members of that population and I estimated the mean age, height, and weight. But I don't know the extent to which these measures are accurately describing the real parameters of the population. And I'm gonna use this idea of real all the time. But I want to clarify that we don't really know what is that real parameter. Because remember that the population is also theoretically constructed to some extent. So I can say, for instance, I want to focus on the, I don't know, children in the United States that are between the ages of 5 years old and 11 years old. But imagine that right now many children are coming in and out of that category. You know what I mean? So how do you know that that real parameter exists? So it's something theoretical, okay? We're gonna try to process this idea a little bit more. There's another way why we need inferential statistics, and is that descriptive statistics is very limited because the world is gray. We learned these perfect figures in which we saw the tendencies very clear with the figures or with the tables, because we want to give you examples that can be understood easily. But the truth is more difficult. Look at this example. So we have here what happened when you control. Remember this comes from the last week actually. So we were talking about how partisanship can be related to support to gun restriction, right? And we said that the Republicans tend to be less likely to support this kind of policies than Democrats, or vice versa, right? But when we control with for gender, we found that male are less prone to support these policies, regardless if they are Democrats or Republicans. And look at this example. What happened here? How do we estimate this effect? So can we still say that okay, can we still say that this is 49. Sorry. Can we still say that that the 3 points difference between Democrats and Republicans is significant in this case? So can we say that despite or regardless gender, Democrats are still more likely to support gun restrictions than Republicans? So how do we know that that 3 point difference is significant or not? Okay, that's the problem with descriptive statistics. We don't really know. We have these figures, we have these tables. Sometimes we have very strong tendencies, very strong lines, or very clear differences between 2 percentile points. But sometimes we don't have that kind of things. And in reality, we tend to have more these kind of examples, like small differences, a lot of nuance, a lot of gray zones, right? For that reason, we also need differential statistics and more sophisticated kind of statistical tools. Okay, but returning to the first question, like how do we know that this statistic is the actual parameter of the population? Accuracy in inferential statistics depends on 3 factors: the random sampling, the sample size, and the degree of variation of the population parameter. Okay? Okay, so in order to rule out sampling bias or sampling a group of members because of a particular variable that we are not paying attention, which, for instance, which can create these compositional differences. For instance, in this group, imagine this group. If I only, if I draw a sample with only members of the yellow group, what's gonna happen? This sample is probably give me or yield biased results because we don't have members from the other groups, and actually the largest group here, which is the gray group, is not represented, right? So we need to use a mechanism that ensures that every member of the population has an equal chance of being chosen for the sample, okay? That's what we call simple random sampling. Sometimes we want to be more, like to have a more strict kind of rule or tool to draw this sample, and we want to draw a particular small sample to some extent of each group or each subgroup of this population. For instance, in this case, if we want to draw a sample of 3 members of the population, we would need to have at least 1 member of each group, or 1 member of each group because we have only 3 members, right? And that's what is called the stratified random sampling. A clear example of random sampling and stratified random sampling is when for a survey they want to be certain that they have women and men, that they have members of different racial groups that are relevant for the survey, or members of different religious groups. So for that reason, they stratify the population according to those groups of interest, and they say we want to run parts of the sample, or better, we want to draw a sample from each one of these groups. Okay. It is critical for the random sampling, the sampling frame. The sampling frame, because as I said, the population is constructed, is theoretically constructed. We need to have a sampling frame, and a sampling frame is a list of, between quotation marks again, all the members of a population. So what do we use to have all the members of a population if, as I said, this population can change all the time? So we can use things like a telephone directory that can be meaningful or significant for a period of time, or we can have a street map, or we can have an electoral register. But what is important to keep in mind is that all these sampling frames can introduce bias, and if we are not paying attention to those potential bias, we can draw conclusions that are to some extent incorrect. And that's what happened with the literary digest, actually. As you remember from the example of Pollock, what happened is that they created I think it was a sampling frame for people who had telephone and cars back in the 1930s. And that was a sampling frame basically of more or less rich people and not all the population. And most of the lower classes supported Roosevelt more than the yeah the rich people in the United States back in that time. Some people, for instance, say that nowadays the telephone directory is not the most powerful kind of sampling frame because almost nobody is using the directory, the telephone right now. So what might be a good sampling frame right now? Maybe the electoral register is still a powerful kind of sampling frame. Maybe the street map can be. Okay. The most important thing here is that random sampling is crucial for inferential statistics. If a sample is not randomly selected, then the other parameters or the size of the sample or other elements are not really important because we cannot assure that we have control or we have been careful with potential selection bias. The problem with selection bias is that sometimes you can identify what are, for instance, this systemic error that I'm introducing to the study, but sometimes you don't know. You don't know why, or you are not aware of those kind of potential bias and you cannot control for them. Okay? But there is a trade-off here. When we use random sampling, we are changing two different types of error. A bad error, between quotation marks, which is the systemic error, for a good error, which is the random sampling error. But there's always going to be an error. That's an important thing to keep in mind. Always that you want to say something about a population based on what you estimated about a sample, there's always going to be an error because you are not completely certain that this actually describes the population. You are more or less certain, okay? And we're going to talk about it. But the good thing about the random sampling error is that we know we can estimate that error. We can know the magnitude of that error. And in such a way, we can even embrace the uncertainty that is related with this error, okay? So we have this formula. For instance, if we want to know the mean of the population in a particular numeric variable, we estimate that mean for the sample and we add to that value the random sampling error, okay? So the random sampling error at the same time has another formula. So we're going to be talking about a lot about formulas here. So it is important to pay attention first to the intuitive level, because if you understand the formulas, what they are trying to tell you about these particular concepts, there's not going to be problem with the mathematical part, because you're not going to do the mathematical part. I'm not going to ask you to do that. But you need to keep in mind what kind of relationships these formulas describe, okay? So when we think about the random sampling error, it is a factor of two other variables, the variation component and the sample size component. And as you can see here, the relationship between the random sampling error and the sample size component is negative. So as the sample size increases, the random sampling error is going to decrease. And the relationship between the random sampling error and the variation component is positive. Thus, if the variation component increases, so if the values in that population, or I'm sorry, in that sample tend to vary from each other, and each of them tend to vary in relation to the mean, so you have more standard deviation, more dispersion, so you're going to have more random sampling error. Okay, it's going to be higher the random sampling error. Okay, and it makes sense intuitively. The random sampling error is basically less precision in our estimation. We don't really know what happened here, so we have a higher variation between the actual or between the different values that I can see in the sample. Okay. Okay, before we move forward, it is important to keep in mind this notation, because you can see this kind of notation in the book, and I'm gonna use it consistently in the lecture and in the slides. So it's important to keep in mind that kind of thing. So when we talk about the size, we use capital N for the population and lowercase n for the sample. To talk about the mean, we're gonna use the Greek letter mu, and we're gonna use x bar for the sample, mu for the population, and x bar for the sample. And when we talk about the standard deviation, we're gonna use the Greek word sigma, and for the sample, we're gonna use the letter S. Okay? Okay, so let's move on. And let's introduce an example as a toy example to use this idea and try to bring these terms to the real to the real world, even if this is a toy example. Okay, so imagine that a billionaire hires you to conduct a survey in the state where he is a representative in the Congress. Okay, he wants to pass a bill against immigration, but he doesn't want to lose the support of his electorate. So he hires you to estimate the mean feeling thermometer about immigrants in the state. And if the electorate support for immigrants is lower than 40 points, he will present the bill. Okay? And he tells you something like this. If you correctly estimate the mean of the electorate support for immigrants, I'm going to pay you $1 million, which is a lot. But for every 5 points further of the real mean, I'm going to subtract $250,000. So it's going to be a lot. Okay, so you want to be precise. You want to hit the target. The closer or be the closest as you can, as close as you can. Hopefully hit the target. Okay, so you want to be very close. You want to be very precise. Okay, so that's just an example. But let's return to this idea. So we're going to explore intuitively this idea of the random sampling error and the relationship with the variation component and with the sample size component. Okay, so imagine that we have that the mu, like the mean of the population for that example of the billionaire is actually 57. So people tend to support the presence of immigrants in the United States, in that state, in the 57 out of 100, being 100 the highest support and 0 the lowest support. Okay, and imagine that the variation of those opinions about immigrants, the standard deviation of that dispersion is 24.8, right? Okay, and you want to, so you hire 10 people and you say to that people, run samples and conduct like a small surveys and tell me the mean value of those surveys. And okay, so you in the x-axis here, you have the size of those samples. So you're gonna conduct 10 surveys of a size of 25 people each survey. Okay. Later, imagine that you I don't know, the next week you say, okay, I'm gonna hire the same 10 people, but now you're gonna conduct 10 surveys of 100 people. And later you say, okay, now you're gonna conduct a survey of 200 people, and later 300 people, and later 400 people. Okay? And in the y-axis, you have the mean that you're gonna find with those surveys, okay? Imagine that the real value, again, of the parameter is 57. And the dispersion of those surveys is 24.8, okay? So we're clear here. This example in the book didn't make sense immediately, but if you get it, it's gonna be great for you because you're gonna understand what does it mean, this idea of precision in the random sampling error, okay? So let's go. So you ask these workers, these researchers, to conduct these 10 surveys with those different conditions, right? And what you found here when they run the surveys with of 25 people or based on 25 people each one, you see this high level of dispersion, and none of the surveys actually hits the target, okay? The next week, you find that at least one of the surveys hit the target and you see less dispersion. So they are closer to some extent to the real value. And the final week, many surveys were actually hitting the target and the dispersion was kind of small, right? So what this tells us is that as you have a larger sample, so you're gonna have more precision, okay? Because your random sampling error is gonna be smaller, okay? Now imagine that you want to do the same, but the dispersion of those opinions about immigrants in the state is lower. So you're gonna have less dispersion, okay? But you're gonna do the same. This is a second scenario. This is another scenario. This is another world. Okay, in this world, again, you're gonna do the same. You're gonna hire 10 people to conduct 10 surveys with the same sizes of those samples, but the dispersion is gonna be smaller, right? In that state, people will be more consistent about their opinion about immigrants, okay? And what do you have here? You have that even with samples small, such as 25 people, some of these samples will hit the target. With 100 people, you're gonna have more samples hitting the target and a smaller range of dispersion, right? And with 400 people, you're gonna have a lot of precision, okay? That's when sigma has a value of 17, okay? So what I want you to have in mind is this idea that there is a shrinkage of the dispersion, and that shrinkage of the dispersion is gonna increase as well the precision of this prediction or of this survey, because the random sampling error is gonna be lower, okay? So both a larger sample or a smaller variation of the opinions of the people will lead me to a smaller random sampling error and to higher precision. So I'm gonna be more precise. So I'm gonna hit the target more precisely, okay? There's another thing that is important to highlight here, and is this idea of the normal distribution or the shape of the distribution. Look, think about this example as a distribution, right? So what you have here is the shape of that distribution. Most of the values are concentrated here in this area, but you see like a high dispersion, okay? That's with the first like a state of the world. This is the second state of the world. So you have less dispersion, right? It's like a more precise, it's more compact, this sample, okay? That's the shape, that's another shape of the distribution. This is the kind of shape of the distribution that we would like to have because it's gonna be more precise, okay? Okay, so that's the intuitive level. Now let's go to the mathematical part.